Hi, I'm Yumna Habib. In this video, I will be discussing Menelau's theorem in hyperbolic and Hilbert geometries. I'll start by going over some brief history about who Menelaus was and what he did. Menelaus was a Greek mathematician born in Alexandria. His area of interest was geometry, and his most famous work was Spherica, which dealt with spherical triangles and their applications to astronomy. He is also known for Menelaus' theorem, which basically states that points lying on three sides of a triangle are collinear if and only if the ratio of the products of the non-adjacent sides is 1. So as you can see in the diagram here, we have a triangle. We extended side BC, and we have a point A prime, and on side AC we have a point B prime, and on side AB we have a point C prime. So all of these points are collinear, meaning they lie on the same line, if and only if the following ratio holds true. So AB prime over B prime C times CA prime over A prime B times BC prime over C prime A, and this product gives you 1. Next, I'll be talking about Menelaus' theorem in hyperbolic geometry. Since we work with different kinds of geometries in math, we use different versions of Menelaus' theorem as well. Before we can look at Menelaus' theorem in hyperbolic geometry, we must define the hyperbolic ratio. So, we have points A, B, and X that are distinct and lie on a hyperbolic line. And their hyperbolic ratio is given by the following. So it's the hyperbolic sine of A and X over the hyperbolic sine of X and B if X lies between points A and B, and it's the negative hyperbolic sine of A and X over hyperbolic sine of X and B for all other cases. And of course, as mentioned, this is the hyperbolic sine function. From this definition, we can see that the hyperbolic ratio of points A, B, and X determines the position of point X relative to points A and B. We are now ready to define Menelaus' theorem in hyperbolic geometry, which is, so we have ABC, which is a hyperbolic triangle, and we have L, which is a hyperbolic line. And note that this line does not pass through any of these vertices. But this line meets BC at point Q, AB at point P, and AC at point R. So, the absolute value of the product of their hyperbolic ratios is 1. We can write this as the hyperbolic ratio of points APB times the hyperbolic ratio of points BQC times the hyperbolic ratio of points CRA, and when we take the absolute value of this product, we get 1. So this is a statement of Menelaus' theorem in hyperbolic geometry. The proof for this theorem is fairly simple and requires knowledge of basic trigonometry. Since we're working with absolute value, we can label the vertices of the triangle ABC in any order and it won't affect our final result. We now apply the hyperbolic sine rule to triangle APR, which gives us hyperbolic sine of AR over sine of angle APR, and this equals the hyperbolic sine of AP over sine of angle ARP. Similarly, when we look at triangle BPQ and triangle CRQ, we get similar relations. From the diagram, we can also see that angle APR is the same as angle BPQ, and angle BQP is the same as angle CQR, and angle ARP is the same as pi minus angle CRQ. This, in turn, means that sine of angle APR is the same as sine of angle BPQ, and the sine of angle BQP is the same as sine of angle CQR, and the sine of angle ARP is the same as sine of angle CRQ. As such, when we put all of this together, we get the desired ratio, which is this. And this concludes our proof. Now, this proof is valid for one case only. It is worthy of noting that there are other cases possible as well, and they all can be proved using a similar method. So, connecting historical and modern geometries, Menelau's theorem has applications in higher level mathematics that further enhance our understanding of important concepts. In fact, the hyperbolic Menelau's theorem has been used to explore new approaches in geometry. One such application is Hilbert geometry, which was introduced by David Hilbert in 1899 and includes natural generalizations of hyperbolic geometry. In order to better understand how Menelau's theorem and Hilbert geometry relate, we must familiarize ourselves with some basic definitions and notation used. So, in Hilbert geometry, we have 2 points AB such that they lie in Rn. Now, the line passing through points AB is denoted by AB, whereas the open segment with endpoints A and B is denoted by AB bar. We are now ready to define the cross ratio in Hilbert geometry. So, we have points A and B in Rn, and they're distinct points. And we also have points X and Y that lie on AB. And we can express these points as linear combinations. So X can be expressed as lambda 1A plus mu 1B, and Y can be expressed as lambda 2A plus mu 2B. So, the cross ratio of A, B, X, and Y is given by mu 1 times lambda 2 over lambda 1 times mu 2, where the denominator cannot equal 0. Using this definition, we can now define Hilbert geometry. So we have H, which is an open, strictly convex set in Rn, such that n is greater than equal to 2. And the Hilbert metric is given by dH such that we have the following. So the Hilbert metric is 0 if x and y are the same point, and it's half times the absolute value of ln of the absolute value of the cross ratio of points A, B, X, and Y. And this is for the case if X and Y are different and the open segment with endpoints AB is an intersection of H and XY. Now, this pair, H and the metric on H, is called the Hilbert geometry in H. From this definition, we can see that the Hilbert geometry lies in the domain of the convex set H. Building on this, we can show that if Menelaus' theorem holds true in a Hilbert geometry, that geometry is also hyperbolic. And the reason behind this is that this specific geometry turns out to be a solid with all sections being ellipses. However, we find that H is an ellipsoid if and only if it is also hyperbolic. And so we can see that the relation holds. This brings my presentation to an end. Thanks for listening, and I hope you learned something new.